Some of the challenges, the biggest challenge actually in this investigation was how to model the connections. Because we learned from the towers too that since we do not design connections for fire effects, basically we do not, especially for shear connections, we design these connections to carry gravity. However, when we have fire situation, these connections will be subjected to gravity load because that load has to go somewhere, but at the same time there are lateral loads due to, here we focus mainly on thermal expansion. Thermal expansion played a huge role in this analysis. That when you have beams heating up, that would put these bolts, for example, in this type of shear connection, what we call thin connection or shear cap connection. This is an elevation view and this is a plan view. These will be subjected to lateral loads, and there is a need for us to model in order to do this analysis right, is how we model the failure of the bolts, the failure of these plates and the welds and bolts and everything under lateral loads as well as vertical loads. Another type that was very common between girders, this was very common between beams and girders. This type of connection is called bearing connection or seated connection. It's again another type of gravity or shear connection where basically the beam is resting on this plate. And in plan view, you can see this is the beam. This is the beam, this is the web of the beam, and this is the bottom flange, and it's resting on this plate. And this plate is supported also on another plate with a fillet weld here. And on the top, this is an erection angle that I'm putting there just to see the connection properly. So we took a lot of care on how to model these types of connections under gravity and under lateral load using a series of what we would call break elements that would be able to account for the failure of the bolts, the failure of these connections in a variety of modes as I will show in the next few slides. For example, this is one of the connections, and you see this is the connection in reality. Bolts here connected, connecting the shear tab that's bolted or welded to the column and bolted to this beam. And this is how we express this in the computer using what we call break elements to account for a variety of failure modes. The stiffness of the bolt and its failure load, the shearing of the plate, what we call block or weld shear, bolt shear, tear out, and all these were basically similar to a spring element, if you know the term, a spring element that can carry force, but its strength and stiffness would drop to zero once a certain criteria is met. So, and we can calculate what's the criteria for bolt shear, for example, and using this criteria as temperature dependent, because there is degradation under elevated temperature, and that will be input to that connection model. That's just one example, but we did a lot of these for a variety of connections that were around the structure, and we end up putting these models in the 16-story model, the ANSYS model, only on the right side of the building, because we knew that the initiating event would correspond to this region based on what we saw in that video. Just to give you an indication, this run, it took almost 6 months. Because of the amount of iterations and conversions problems that you will see in these types of analyses. So it was very prohibitive for us to use this connection model all around the building. But we put it on the right, on the east side, as you can see here, for all the floors that were affected by fire. For the LS Dyno model, the model that captured the behavior from the initiating event all the way to collapse, we used shell elements mainly with, again, simple or similar representation of the connection behavior and failure. Failure modes, and I mentioned that early on, they include shear stud failure. These are the shear studs I mentioned earlier. They are sitting welded to the top of the steel beam and embedded in concrete to provide for the composite action. Bucket beams and girders, connection failures, concrete slab, crushing or cracking under tension. This is the ANSYS model, again, 16-story model. included close to 100,000 nodes and 100,000 elements, and captured all of the behavior in the fire zone during the time of interest to us. And this is the bigger 47-story model using LS-DYNA that captured all the way the response from the initiating event that I'll be speaking about soon all the way to collapse. Probable collapse sequence. I will be embedding the results of the analysis along with the probable collapse sequence summary that I'm providing here. WTC-2, the south tower, did not cause any damage to World Trade Center 7. World Trade Center 1 damaged 7 exterior columns on the lower floors of the south and west faces and initiated fires on 10 floors between floor 7 and floor 30. And you can see here a picture showing the damage to, this is the east face, we're looking here to the, I'm sorry, this is the west face. And I'm showing here the damage to these columns on this side. We looked very carefully at a number of pictures that were provided to us to provide guidance for the fire modeling and for the structural modeling as what columns were lost, what windows were lost, because the window breakage is crucial for the fire dynamic simulation because it affects ventilation and as such affects the growth and spread of fires. So wherever you see red here, this is the south face, this is the west face. This indicates damage to exterior structural steel, and you can see some of them actually happening here at the top, and all the facade damage, window glass broken, all that was included in this type of graphics in order to facilitate the modeling process. This is the damage that we imposed on the LS-DYNA model, the big model, the 47-story model, and basically at each floor, based on these pictures, you can figure out different damage pattern based on the pictures. So that's what the collapse of the towers did to building 7. Then now we talk about the growth and spread of fires. The sustained fires, as I mentioned earlier, were concentrated on floors 7 to 9 and floors 11 to 13. And as I mentioned, we started in the southwest corner. They took different paths until at the time of collapse, they were concentrated in the northeast corner. And you can see some of these fires raging here as you can see the smoke associated with it. The local fires on the upper floors were not observed after 1 o'clock. And these are some examples of the fire. I think what I'm showing you the north face, if I'm not mistaken. And you can see the fires here on multiple floors. This is like 50 minutes before collapse. This is what we call the initiating event. Initial local failure for collapse initiation. The fire-induced thermal expansion of the floor system surrounding column 79 led to the collapse of floor 13, and I explain the next slide how did this exactly happen. So around column 79, some of these floors, some of the connections next to column 79 failed and led to the collapse of the floor in this region. Remember that the floors underneath are also under fire and they are weakened. So that created a cascading failure of these floors below floor 13. Once that happened, column 79 became laterally unsupported. We know that from structural mechanics that for our building construction, we rely on the floors to provide lateral support for the columns. Otherwise, the buckling length would be tremendous. So in this case, there was a collapse north of column 79 by the floor, and that floor resulted in cascading floor failures underneath that left column 79 unsupported for all these length, multiple floors, and that led to the buckling of column 79. And that was the initiating event. And you can see here in this picture, this is column 79, and these floors had no lateral support whatsoever. Some of them had partial support, means connection failed in one direction but not in all directions. The question now in your mind is, what initiated that floor collapse. This picture showed column 79 in one of the floors obtained from the Port Authority, and this is just a blow up of this corner here. This is column 79, and this is the girder north of it. And this shows the seat that this girder is supported on with 2 bolts at the bottom. And you can see fireproofing is definitely there on the beam, on the girder, I'm sorry. So what we found from these analyses that accounted for thermal expansion and thermal degradation due to elevated temperature and accounting for all possible failure modes is it's likely that shear studs between those beams and the complete slab failed under differential thermal expansion between the beams and the complete slab. Remember that this girder didn't have shear studs, but here these shear studs failed early on in the analysis under differential thermal expansion between floor beams and concrete slab. And that led to the thermal expansion of these beams freely. These beams, you can see here, the exterior wall here is very rigid because the span between each 2 columns is small. However, this side is more flexible, especially there are no beams that are resisting the thermal expansion. When these beams want to thermally expand, this side is rigid, so they expand and push against this large girder. As a result, the girder was pushed laterally by thermal expansion of these floor beams due to one-sided framing. We call this an asymmetric planning, and we believe that this was a large contributor to this collapse. This girder here, it just has beams from one side. There is only this minor beam here, but it has only framing coming from this side, so these beams can push the girder laterally, and this girder can move with it. So the girder was pushed laterally by the effects of thermal expansion, and ultimately, once you keep pushing on this girder, you can see that the forces from thermal expansion moved the girder here and broke those 2 seats, the bolts to the 2 seats, and that girder became unsupported vertically. If you keep pushing it against the seat, at one point it will move from the seat and just drop. And that will start the floor failure in this region. In our models, we observed that this failure first happened at floor 13. Floor 13 collapsed in this region. The floor underneath was already heated. Fires were in the same location. They were weakened. They got this additional load from the floor above, dropping on them, and they're already under pressure. So that triggered a cascading floor failures in this region, and column 79 became unsupported, and that resulted in the column being buckled and unstable. Just to show you, okay. Floor 13 collapsed, followed by a number of floor failures, and now you can see that column 79 became laterally unsupported and buckled because of that. LSD.